We've all been there, right? You're sitting on a packed commuter train, maybe you're rushing to an important meeting, or honestly, you just want to get home after a long day. And then, bam, you grind to a complete halt. Those agonizing minutes just kind of tick by. Then you hear it, that muffled, slightly static voice over the speaker apologizing for the delay. It is so incredibly frustrating. You probably sigh, roll your eyes, maybe check your watch. But what if I told you that this exact moment of pure, unadulterated annoyance is actually a perfectly orchestrated, life-saving maneuver? Welcome to This Explainer. Today, we're diving into a total paradigm shift in how we look at these seemingly endless railway delays. Okay, let's really dive into this. Think back to the last time your commute was thrown into total chaos by some mysterious infrastructure issue. You're staring out the window, just wondering, why on earth does a tiny, seemingly insignificant equipment glitch bring a massive, heavy-duty railway network to an absolute standstill? It's crazy to think about, right? A modern railway is this colossal web. Thousands of moving parts, signals, switches, and sensors. So when a single, random broken component stops trains literally miles away, well, it feels like a huge system failure. It really feels like the technology is just out to get you. Usually, the culprit boils down to two dreaded words: signal failure. Ugh. Just hearing that phrase is enough to make any daily commuter shudder. It's kind of this universal, shared experience that unites us all in sheer annoyance. And look, I totally validate that frustration. But here's the fascinating secret. That super frustrating moment, that supposed failure, is actually a brilliant engineering success. Seriously, it is doing exactly what the system is supposed to do. The train isn't stopping because the system is broken, it's stopping because the system is working perfectly. So the secret behind all of this lies in a foundational engineering concept called the fail-safe principle. In the world of complex safety engineering, the underlying philosophy is entirely different from how we build, say, everyday consumer electronics. Engineers actually fully expect equipment to malfunction. They know it's going to happen. Moving parts wear out, power grids fail, copper cables snap. It is just a statistical inevitability. And because they know things are going to break, the entire system is meticulously designed with one foundational rule. If a fault occurs, literally any fault at all, the equipment will automatically default to a restrictive, safe state. We aren't just designing equipment to work safely, we're deliberately designing it to break safely. And this brilliantly illustrates the concept. Just look at how a classic mechanical semaphore signal works. During normal operation, the signal arm points downward, letting the train driver know the path is clear. But check out that heavy counterbalance weight at the bottom of the post. The system literally uses the inescapable force of gravity to protect you. If the operating wire that connects this signal to the control box suddenly snaps, well, that heavy weight immediately drops. Gravity just yanks it down, and through a mechanical pivot, it automatically forces the red signal arm right back up into the horizontal danger position. The failure of the wire directly, physically causes a safe outcome. I mean, that is the pure genius of inherent fail-safety. Now, obviously, most modern railways aren't using long wires and heavy iron weights anymore. They use electricity. But the exact same logic applies to the classic electrical signaling relay. Think of it as an enclosed, transparent box that acts as the absolute heart of electrical signaling safety. Instead of a mechanical weight, this little guy uses an electromagnetic coil. When power is flowing smoothly, the electromagnet pulls a metal armature, which is basically a small switch, upwards, closing the circuit and giving the train a green proceed signal. But let's say there's a sudden power cut, or a wire breaks, or a system crashes. The coil instantly loses its magnetic pull. Boom. Gravity and spring pressure immediately force that metal switch to drop, physically breaking the circuit. It even uses special silver and carbon contacts that physically cannot weld together under an electrical surge. So the system requires constant, active energy just to give you a green light. The exact millisecond that energy is lost, you get a red light. So what does this actually look like out on the tracks? Well, when we talk about the operational effect of a fault, we're talking about massive, immediate, network-wide reactions. The millisecond a fault is detected, maybe an electrical track circuit loses power, or a switch loses communication. Several things happen all at once to enforce that restrictive state. Signals instantly default to red, screaming danger to any approaching drivers. Track circuits falsely show up on the control board as occupied, basically tricking the computer into thinking there's a ghost train parked on the broken section. And track points, those movable sections of rail that physically guide trains at junctions, they are strictly locked down and prevented from moving at all. The system safely and aggressively halts all nearby traffic to prevent any possibility of a collision or derailment. Let's move to the bigger picture and see how this builds up. These physical and electrical safeguards form the foundation for the complex digital networks we rely on today. Engineers pull this off using 3 specific layered methods. First up, as we just saw with the gravity weights and relays, is inherent fail-safety. The physical components naturally default to safe states if they break. Second is composite fail-safety. You'll see this a lot in modern computer processors, where multiple independent computer channels are calculating the exact same info. They have to completely 100% agree with each other to let a train proceed. If even one computer disagrees or spots a math error, they cancel each other out and safely shut the whole operation down. And third is reactive fail-safety. This is where a single component is heavily monitored by sensors, and any hazardous fault is rapidly detected and shut down before an accident can even think about happening. But this brings us to an incredible, actually kind of painful engineering dilemma: the massive trade-off between high safety and low reliability. Because the system is specifically designed to forcefully shut down at the very slightest hint of an anomaly, it achieves a ridiculously high level of safety. But, and it's a big but, this hypersensitivity massively hurts system reliability. If a sensor gets just a tiny bit dirty, if a single LED bulb burns out, or hey, if wet autumn leaves disrupt an electrical current on the rail, the system panics. But it panics in the best way possible. It completely stops everything. So a perfectly safe equipment failure still results in stopped train traffic, infuriated customers, and massive delays across the entire city. You are quite literally trading reliability to guarantee your safety. And that brings us to this incredible irony, which is probably best captured by a core principle of safety engineering. Being open to human error, manual procedures are inherently less safe. Think about it. When this ultra-safe, highly automated system stops working, even if it stopped perfectly safely, we still have to get those trains moving eventually, right? To do that, human control operators are forced to step in. They have to use manual procedures. They're out there talking to train drivers over the radio, granting them special verbal permission to slowly creep past a red light. But by doing this, actually, scratch that, it's more like by having to do this, we bypass the safety system and introduce the exact human error the automated network was built to eliminate in the first place. Which leaves us with this final, incredibly provocative thought. If a super safe system is so sensitive that it fails frequently, and those frequent safe failures force us to rely on inherently dangerous human manual workarounds just to keep the city moving, how do we actually balance the risk? It is a super delicate tightrope that safety engineers have to walk every single day. So the next time your train abruptly stops in the middle of nowhere and you hear that dreaded signal failure announcement, take a deep breath. You aren't just experiencing an annoying delay, you are sitting safely inside a brilliantly complex, life-saving trade-off